Okay, on Blackboard, there's a little survey here. Maddie is going to have some like tutoring slash office hour kind of things in the evenings when I imagine you guys are probably more free than when I have my office hours here. Um, so just do this little survey on Blackboard Tuesday, Wednesday, or Thursday evenings. You can pick all of them or one of them or anything like that. But for on Monday, we'll figure out the results and announce when he's going to hold those hours. So do that when you get a chance. Okay, everybody turn in their homework. Sorry, I had to do it to the people that's no, I had to make sure that everybody's heart skipped at least a little bit. I was already thinking about tomorrow's lecture in Bluffton, so JK. Sorry. Okay. Also last night I posted the answers to the all the other problems for the homework as well. Okay. So this chapter is about acids and bases. So you should be sort of already a little bit familiar with acid-base chemistry from Gen Chem. And we're going to review that briefly, but a lot of this stuff is going to look a good bit different from the acid-base chemistry in Gen Chem, especially Gen Chem 2, because so the first thing you probably hopefully learned about a couple different types of acid-base theories. The one we're going to start with and spend most of our time on today is Bronsted-Lowry. There's Arrhenius, which is the most restrictive definition, or the smallest definition. Then Bronsted-Lowry is a little bit broader than that. And then Lewis acid-base definitions are even broader than that. And we'll get to that at the end. So, what are the Bronsted-Lowry definitions of an acid and a base? Well, an acid is a proton, what? Acceptor or donor? Acid is a proton donor, and then the base is a proton acceptor. Dr. D'Antonio, come on. All right. So an example of this would be hydrogen chloride. Notice I'm calling it hydrogen chloride and not hydrochloric acid because what we're going to make is hydrochloric acid. Hydrogen chloride reacts with water. To give us chloride, Cl minus, and the hydronium ion, H3O plus. So based on our Bronsted-Lowry definitions, okay, well, the first one's kind of obvious. Which one is the acid? HCl, right? Hydrochloric acid. All right. So that leaves water as the base, but let's make sure that that's true. So let's look at what the proton is doing, or a proton. So I think we can see from HCl to Cl minus that chlorine atom is losing a proton. Okay, so that's going to be this proton that's leaving. And then what about the water molecule? Well, the water molecule gains a proton. And I mean, all three of these protons are identical, but we'll call it the one on the top. That's where it looks like it appears. And so this pink proton is the one that is donated slash accepted in the acid-base reaction. Okay, so Acid is a proton donor, HCl is our acid, and yes, it's donating that proton. What's accepting the proton? Well, that's the base. So the water is accepting the proton to become the hydronium ion. So the water is our base. And the cool thing about water is it can act as an acid or a base, not at the same time, but in different reactions depending on the conditions. It's called amphoteric. It can act as an acid or a base. Okay, I've drawn this as an equilibrium reaction. And so if we're able to label the acid and the base going in the forward direction, we should also be able to label an acid and a base going in the reverse direction. And we can, but we give them very slightly different names. So what about the Cl minus? What is that doing when we're going leftwards? Well, it's accepting a proton to become HCl. Okay, so that means the Cl minus, I'm leaving intentional space here. The Cl minus is acting as a base in the reverse reaction. And okay, by process of elimination, H3O plus should be our acid. Acid is a proton donor. And yes, it's donating the pink proton to the Cl minus to make HCl and H2O. Now, to prevent confusion between like which direction we're talking about, the forward reaction, the labels for the forward reaction, we just use acid and base, but for the reverse reaction, we use conjugate acid and conjugate base. One thing that's important to notice here is that the acid becomes the conjugate base and the base becomes the conjugate acid. And that has to be the case because if the reaction is going to go back and forth, as it does in an equilibrium reaction, you can't have one molecule acting as an acid every single time. That would mean it's donating a proton every single time, and eventually you're going to run out of protons. So the acid becomes the conjugate base, and the base becomes the conjugate acid. We could also refer to, so these terms aren't specific to this reaction. You could say just in general, in a vacuum, that chloride, Cl minus, is the conjugate base of hydrogen chloride, or that hydronium is the conjugate acid of water. Those two statements are always going to be true regardless of what reaction you're doing, regardless of if you're even treating HCl as an acid and water as a base, which you might not actually. But when they're together, that's going to be the case. All right. Another example. Okay, I'll be good and add my lone pairs in. You should do this too. Okay, what about this reaction? The ion on the left, is that our acid or base? So based on our definition, what is it doing between the beginning and the end of the reaction? Is it donating or accepting a proton? Accepting a proton. So this is our base. Water is an acid proton donor. Yes, it's donating a proton to go from H2O to OH minus. And so let's label our proton. There it is. It's moved from the water to the tert butoxide. That's what that's called, tert butoxide ion, to give tert butanol and hydroxide. So assigning conjugate acid and conjugate base, we could either pretend that we're going to do the reaction in reverse and use those definitions, or we can say, all right, well, the acid becomes the conjugate base and vice versa. All right, so the acid, water, is becoming the conjugate base, and the base is becoming the conjugate acid. Whether the acid or base is organic, as in like has a skeletal structure drawn in, or is just not organic or inorganic, if you like the one on the top, that doesn't matter. Well, it very indirectly matters, but that doesn't matter really for assigning acid or base. Okay, we can make a generalization of this acid-base conjugate thing by using water as an example. So this is sort of a summary of this stuff. So if we take water and we add a proton, that's going to give us H3O plus. In that process, water is a proton acceptor. So water is acting as a base. And the result of that reaction is the conjugate acid of water, which is H3O plus. We can go the other direction and instead subtract a proton, or should I say donate a proton from the water? If we're losing a proton, we're going to OH minus. So water is acting as an acid in this case. And then the OH minus is going to be the conjugate base of water. You can replace the water with any molecule. You could use ammonia, you could use acetic acid, you could use anything you like. And this will always be true. If you add a proton, the substance is acting as a base and you form the conjugate acid. If you subtract a proton, the molecule is acting as an acid and you end up with the conjugate base. So we've talked about where the hydrogen atom goes. But what's even more important than talking about the proton is the electrons that make the bonds between the proton and whatever the molecule is. And so we're going to show that using reaction mechanisms, which are an extension of the resonance curved arrows that we talked about. So this time we're going to use curved arrows again. But they're actually going to show the movement of electrons rather than just being a bookkeeping method to show how you kind of get from one resonance structure to the next. So it's for real this time. The way you draw the arrows is the same, but we don't have all of the rules that are that kind of box you in when you're doing resonance structures. There's still rules though. So these reactions that I've shown you they have a name and it's really creative. Proton transfer, because a proton is being transferred. And a key for this, when you're drawing a mechanism, is you need at least two curved arrows in order to show the movement of electrons correctly. And the whole reaction scheme, including the arrows that show the movement of electrons, that is the reaction mechanism. So from resonance structure drawing, this part's going to be the same, that the tail of the arrow is the source of electrons. And the head of the arrow is the destination. So we've got to start where the electrons are and then use the arrow to show where they're going. Okay. Here's another Bronsted-Lowry acid-base reaction. So I think we can see the base because we have OH minus, and that's like sodium hydroxide or potassium hydroxide. And I think we know that pretty well to be a base. The other molecule, well, it conveniently has acid in the name. It's acetic acid. And then the base becomes the conjugate acid becomes the conjugate base. So the OH minus becomes water, so this is the conjugate acid. And that's the conjugate base. Now, we sort of did the cheating method here to figure out what these were, but we can also check the proton transfer part to see if our assignments are correct. So what proton is being transferred? Okay, so the base accepts a proton to become the conjugate acid. All right, so this proton that's shown up, that's the proton that's transferred on that side. And then the acid loses a proton to become the conjugate base. And so there's our proton at the beginning. Okay, the acid is a proton donor. Yep. And the base is a proton acceptor. Yep. Also, it's not a coincidence that the pink hydrogen is on the acid in both cases. So now we need to show the curved arrows that describe that process. And these curved arrows, we're only going to draw them on the left-hand side, but they should allow us to predict the products on the right, even if we didn't have them there. So we need to make a bond between the base and the proton, and we need to break a bond between the acid and the proton. Okay, in resonance structures, we weren't allowed to make or break sigma bonds, but in fact, that's the only thing we're going to be doing in this mechanism is making and breaking sigma bonds or single bonds. So the connection between the proton and what used to be the base, now the conjugate acid, is that OH bond. And so the electrons are going to come from the oxygen and go to the proton. Okay, that forms our first sigma bond. That bond. And then we need to break the bond between the proton and the acid oxygen because that bond is not in existence in the conjugate base. And so we show the electrons from the bond moving toward the oxygen. So in both cases, the tail of the arrow is starting at a pair of electrons. From the arrow on the left, it's starting at a lone pair. And the arrow on the right, it's still starting from a pair of electrons. It's just a pair of electrons that are in a bond. A common mistake is to try and draw the arrow coming from the hydrogen, something like that, where it goes toward the oxygen. You can't do that because the hydrogen, well, it's a proton, H plus, it doesn't have any electrons. And so you can't draw an arrow from somewhere that has no electrons because the arrows are showing the movement of electrons, not the movement of atoms. Okay, it should be kind of obvious from this example, but proton transfer must involve both an acid and a base. And that's by the Bronsted-Lowry definition because the acid is a proton donor and the base is a proton acceptor. So in order to transfer a proton, something has to donate the proton, something else has to accept the proton. So there's always an acid and a base going on. If you can't identify them, I mean, you should be able to identify them, but don't say, oh, I just have a base in this reaction where there's a proton transfer. No. The other thing is an acid. You just need to look and see that, oh, the acid is donating the proton, so that's an acid. Even if it doesn't have acid in the name, this one's easy because it has acid in the name. And then hydroxide, I think we all know that that's a base, but there's other bases that don't look as basey. Okay, some terminology that we use sort of colloquially to refer to this stuff. We will say that the base, it's not colloquial, it's legit. The base deprotonates the acid. Okay. Yep, the base is taking a proton away from the acid, so it's deprotonating the acid. And in reverse, the acid is deprotonated by the base. If you're a bit of an English nerd, you'll notice that in both of these phrases, the active subject of the phrase is the base, right? The base is doing the deprotonating in both cases. And kind of a way you can translate that into the arrows is the arrows always start at the base, right? The base has the electrons. The electrons are what are actually doing the chemical reaction. And so the arrows have to show that process. So the arrows should start at the base. Okay, the base is all, for our purposes, the base will always have a lone pair of electrons that it uses to grab the proton from the acid, to deprotonate the acid.
Or are you just using protonated at the pink point in this, or is it always deprotonated?
Um, you can say that the acid is protonating the base. That's also correct. The reason I wanted to highlight this is because it's important that your arrows come from the base and go to the acid. Okay, so let's do the HCl example. Actually, you do the HCl example. You'll notice I haven't drawn the plus signs, and that's pretty common when we do mechanisms, just to keep everything a little less cluttered. It's not a requirement by any means, but a lot of times you want to draw an arrow that kind of gets in the way. So we already did this. So acid base, conjugate base, conjugate acid. So show me the arrows. Okay, does our first arrow start on the HCl or the water? So we started with the base and drew an arrow to the acid. All right. So let's start at the base and draw an arrow to the acid. Okay. Actually, first let's identify what proton we're going to be transferring. So the acid donates a proton and becomes the conjugate base. So that's the proton on the left side. The base accepts the proton to become the conjugate acid. So this is the proton that's being accepted. Again, all three of those protons are identical, so it doesn't matter, but okay, so now we need to draw or show one of the lone pairs on the oxygen atom of the water deprotonating the acid. And so the arrow is going to go from the lone pair here to that hydrogen. Okay, we've sort of hopped over the quote. That's okay, that's legal. And then we need to break the bond between the pink proton and whatever it was attached to on the acid. In this case, it's the chlorine. And so we're going to break that bond, and then the electrons are going to go onto the chlorine atom. And if you're given the answer, the products of the reaction, you can check your work 100% of the time, and you can make absolutely sure it's correct. So the oxygen is using a lone pair to make a single bond to the hydrogen. All right. Yes, that is correct, because the oxygen is now down a lone pair. And well, that's the lone pair right there, but now it's in a single bond to the pink hydrogen. Okay, so that arrow is correct. Here, the chlorine has 3 lone pairs and a single bond. That single bond is breaking and the electrons are coming onto the chlorine. So we should expect it to have 4 lone pairs and no single bonds, which is what we see. Okay, and then the charges, you can use your formal charge cheat sheet for that. And you should notice that we're starting with 2 neutral compounds, and then the overall charge on the products is net 0. So we've conserved charge. Questions on how I came up with those arrows? All right. In most, if not all, acid-base reactions, Bronsted-Lowry acid-base reactions, we want to be able to compare the acidity of multiple substances. We might also say to compare the basicity, but it kind of ends up being the same thing, of multiple substances. So actually, I'm just going to take this reaction up here and simplify it to HA plus H2O. I know I didn't draw an equilibrium arrow. That was me being lazy, but that's okay. So there's an abbreviated version of that reaction. In this case, A is just chloride, but it could be anything else. It could be bromide, it could be acetate, it could be whatever you like. So if you remember from equilibrium with an M, from Gen Chem, equilibrium means that there's no change in the concentration of reactants or products. It's not that the reaction has stopped, okay? It's that the rates of the forward and reverse reactions are equal, and so it looks like the reaction has stopped because there's no change in the concentration. So when we're using, you probably and this would be Gen Chem 2, you probably used KEQ as as a measure of the position of equilibrium. When we're in water, we can actually simplify KEQ to Ka, subscript A for acid. To denote the position of the equilibrium. I'm not going to make you do math, but you have to see how this works. So this should look kind of familiar. Ka is going to be the products divided by the reactants. And we ignore water because if we're in an aqueous solution, right, we have a crap ton of water. And so the concentration of water is always, it's like 55 molar or something. It's really high and it really doesn't change. And so we just ignore it because chemists are lazy. So you could put actual values in here and find a Ka. Generally speaking, people have already done that for us. And so we're going to need to use a table of values. So generally speaking, Ka ranges from 10 to the minus 50 to 10 to the plus 10. So huge range of Ka values, 60 orders of magnitude, which is 60 decimal places. And to make things a little bit easier on us, instead of using Ka, we're going to use pKa, which is just like pH instead of just the concentration of H. So, by the way, this is lowercase p, capital K, technically it's italicized if you're a typesetting nerd, and lowercase subscript a. But if you just write pKa, I'll know what you're talking about. So pKa, kind of like pH, is negative log of Ka. That should look familiar. And so really what this just does is allows us to play with the exponents only. So that gives us pKa ranges from minus 10 to plus 50. And like with pH, lower number means more acidic. So a pKa of minus 10 is a really strong acid. And a pKa of 50 is a very weak acid. These are not absolute ranges. You can have pKa's below minus 10 and above plus 50. But most compounds that we'll work with fall in that range. Okay, go ahead, bring up Blackboard if you have it. Under the resources folder, there should be this PDF, which is pKa values. So pKa values, right? The subscript A is for acid. So pKa values are always describing an acid and not a base. Okay. So here's a list of some various acids. Some of these should have R groups on them, but anyway, some various acids and their pKa's. So low pKa means strong acid. High pKa means weak acid. Sorry, spoiler alert. That's the answer to one of the next questions. So, shocker, sulfuric acid, H2SO4 is a very strong acid. And the reason that I've listed the conjugate base here is because some of these molecules have multiple different kinds of protons. So this protonated acetone here, it's got other protons. It's got hydrogens here and there. But we want to be very specific here with the fact that the proton that has the pKa of minus 7.3 is the one attached to the oxygen. So when it comes off, you get a conjugate base of just plain acetone. So technically, pKa's are describing individual protons. But in practice, when we say, oh, the pKa of acetic acid is 4.75, we're talking about the most acidic proton because that's the most reactive proton. And if we do an acid-base reaction, that's the one that's going to react. This will be given to you on the exam, so you don't have to memorize it. Just become familiar with it. If there's, okay, you don't, I mean, I'm still going to give it to you, but you should memorize it, and that's water. Water is 15.7. And then that's in comparison to alcohols like ethanol, which are 16. So water just below 16. If you remember anything, remember 15.7. And then down here at the bottom, we've got so these acids here on the we don't really think of these as acid. Is ammonia an acid? No. No, that sounds stupid. And yes, it's an extremely weak acid with a pKa of 38. And then the opposite goes for the conjugate bases on the other side. For example, acetone, we don't really think of acetone as being much of a base. At least I don't. Water is fine, whatever. It's not a very strong base, but and then we get down to stuff like hydroxide, which is fairly strong. And then here's a whole list of bases that are stronger than hydroxide. I think in general chemistry, we think that like sodium hydroxide is the strongest base, and it is the strongest commonly encountered inorganic base, but we've got all these other bases that are even stronger than hydroxide and end up being quite useful in some cases. So there's our pKa chart. Okay, so here's two compounds, and based on pKa, which of these is more acidic? So these specific compounds are not listed on the chart. But some analogs of them, so compounds that are very similar, are. And so we can make a rough approximation of pKa. And also remember that pKa is on a log scale. So if a molecule has a pKa of 10 and another molecule another molecule has a pKa of 11, right? They're separated by just one pKa unit. That's 10 times. A pKa of 10 is 10 times more acidic. I shouldn't have picked 10. Oh well. A pKa of 10 is 10 times more acidic than a pKa of 11. So you just need a very, very small difference in pKa values. Okay, so this one, the amine with an NH2, what is that most similar to on our pKa table? That would be ammonia. Okay, because we've just replaced the hydrogen with that butyl group. Was it a butyl group? Propyl group, sorry. And the pKa of ammonia is 38. So we'll just go ahead and assume that the pKa of this is roughly 38. Could be 37, could be 39. In this case, it's not going to matter. Okay, and then we have this alkyne carbon-carbon triple bond. And let's see where that is. Okay, and here's our alkyne. This is acetylene with a hydrogen on both ends. But we can say that the pKa of our molecule here is probably about 25, 26, 27, 24. So between the amine and the alkyne, which is more acidic? So pKa goes from the lowest number being the strongest acid to the highest number being the weakest acid. So that's going to be the lowest pKa, which is 25. So that makes the alkyne a stronger acid than the amine. Questions on the pKa chart? Cool. Yes.
Protons that we're taking off, like when we go back to the chart.
Sorry. Yep.
Like, when you're like down at the bottom with the multiple like hydrogen atoms.
Yes.
Where it's take off.
And this, so for like ethane at the bottom, this is just CH3, CH3. And all 6 of those protons are actually identical, so it doesn't really matter which one we remove. If there's, if there's more asymmetry in the molecule, then yeah, we're going to have to decide which of those is more acidic. And we'll talk a little bit about those rules later. Maybe not for examples exactly like this, but yeah, those are all the same in this case. Okay, so you might think that for comparing bases, we need a table of pKb values, B for bases, and that does exist. You can look one up, but they're pretty useless because you can get all that information from a pKa chart, and so you just need one set of numbers to deal with. So how do we compare 2 different bases? First, we want to write the conjugate acid of each base. Then we look those acids up in the pKa table or approximate them in the pKa table, compare their pKa's. And then here's the catch, because we're looking at bases. That is the weaker acid. Or let's see, I should say the weaker conjugate acid. The weaker conjugate acid is the stronger base. Okay, so comparing these 2 bases. First, we need to write the conjugate acid of each one. And so we'll do this by, well, a base is a proton acceptor. So we're just going to allow each of these bases to attach a proton where they have their lone pair and the negative charge. So proton there. And proton there. So now we look up the pKa values of those 2 conjugate acids. And so I don't have to flip back. Somebody tell me the first molecule. What's the pKa of that one?
9.
9? Yep. And the second molecule, acetone. And just acetone, so not protonated acetone. Yeah, 19.2. Okay, so the weaker conjugate acid is the stronger base. Okay, so this 9.0, that's lower than 19.2, so this is a stronger conjugate acid. This is a weaker conjugate acid. And so this is the stronger base. Another way you can sort of keep this straight is a molecule can't be good at two things at once. So it can't be a really strong base and a really strong acid at the same time. If it has a strong conjugate acid, it's going to be kind of a weak base. And if it's got if it's a strong base, it's going to have a weak conjugate acid. Just make sure you don't get these two either confused or like mixing the two methods, because that can be kind of dangerous. Okay, so in chemistry, we really like to be able to predict reactivity, and we can use eat lunch. We can use pKa values to predict where the equilibrium is going to lie. For example, in one of these, well, I didn't draw that as an equilibrium reaction, but I'll fix that, I guess. There we go. We can decide which way that equilibrium lies. Thank you. Okay, so how do we do this? First, we need to figure out which is the acid on each side of the equilibrium. Then we compare pKa's. You could identify the base on each side and then draw the conjugate acid of that base, and then, but why? You don't have to do that. Just look for the acid on each side. And then here's the key for equilibrium. We're going to favor, right? An equilibrium reaction just in general favors the lowest energy, most stable side, right? That's how it works here too. We're going to favor the side with the weaker acid, with the more stable acid. In between here, I'm going to draw these tiny little equilibrium arrows because I'm going to expand one that ends up being the correct answer. So that's why it looks weird like that. Let's do the mechanism just because we can. So regardless, we need to determine what's an acid and what's a base. So where is the proton that's being moved? Well, the oxygen is picking up, sorry, the carbonyl oxygen is picking up a proton. So that's the proton on that side. And then the H3O plus is losing a proton to become water. And so there it is on that side of the equation. So the acid always has that pink proton on it. So the base is a proton acceptor. Yep, it's accepting a proton from the acid. And the acid is a proton donor. It's donating its proton to the base. Okay. Well, let's do the mechanism. So arrows start at the base and deprotonate the acid. So that's going to show this bond being formed. That one right there. And then we need to show the bond between the acid and that proton breaking. And those electrons are going to go on to the oxygen atom. And that's what we see in the products. We formed a bond between the base, it used to be the base, and the hydrogen, the proton. And then the acid has one of those the second lone pair has come back down from that bond, or that bond has moved onto the oxygen to become a lone pair. Okay, so now we've identified the acid on each side of the equation. Now we need to compare pKa values. So pKa of H3O plus, and then the pKa of this protonated acetone molecule. H3O plus, what's the pKa of that?
-1.74.
Yep. And the protonated acetone? Minus 7.3. Okay. So lower pKa means stronger acid. These are negative numbers. So minus 7.3 is the stronger acid. And so the equilibrium favors the side with the weaker acid. So the weaker acid is here. So the equilibrium will favor that side. And so that means that our equilibrium arrow points toward that side. Eventually, it might start to become a little bit second nature when you just look at the reaction and you look at the two, generally it's the two charged ions, and you see which one kind of looks happier. I certainly don't expect you to be able to do that at this point, but sort of by the end of Organic 2, hopefully you won't need to do all of this analysis and stuff. Okay, let's do an example. Okay, so tell me, or fix the equilibrium arrow to show which direction that reaction will want to go. Okay, phenol, is that the acid or the base? Yep, acid. So that makes the phenoxide ion the conjugate what? Base. Okay, so we need to compare our acids and their pKa's. So what's the pKa of phenol? 9.9. And water is 15.7. So what did you say? No, I'm curious. I didn't hear. That's hydronium. That's a good mistake because other people are going to make it too. So okay, so between phenol and water, which is the stronger acid? Phenol. All right, so the equilibrium favors the weaker acid, and so equilibrium is going to go to the right in this reaction. So this is really important when you're doing synthetic chemistry, kind of like the labs that we'll do in the second half of the semester and next semester. Because let's say you have acetone and you want to find some sort of acid that you can use to protonate the acetone. And you say, okay, well, let me use some sort of form of hydronium. Is that going to work? You do this analysis and no, the equilibrium is going to favor the products. So you need a stronger acid than H3O plus to protonate acetone. Or let's say you have phenol and you want to make the phenoxide ion. You need a base to do that. And you have some sodium hydroxide sitting around and you're like, okay, is that a strong enough base to deprotonate phenol? You do this analysis and find, yes, hydroxide will work. The equilibrium favors the products. So this is in the lab, this is how we decide what reagents to use. Questions on equilibrium? Cool. Next time, we're going to talk about how to predict this stuff without looking at the pKa values. There's a way to do that. So you don't even need to use the table. All right, see you Monday with your homework.